Hello everyone, this is Dr. Burke and we're doing geometric optics for Physics 1200. The first thing you have to realize in order to understand this lab is that if you have a region of air here and a region of glass, and a light ray travels through the air and hits the air-glass interface, that light ray does not continue to go straight. It gets bent. It gets bent toward the perpendicular here. This is the perpendicular. So as the light ray comes in, it gets bent by the glass. And that phenomena is called refraction. And the index of refraction of the air times the sine of the refractive angle for the air, which is this angle right here, is equal to, this is equal to the refractive index of the glass times the sine of the refraction angle for the glass, and that would be this angle right here. And this is called Snell's law. But refraction is the physical phenomena that governs geometric optics, and we're just going to use the fact that light bends glass. Excuse me. We're going to use the fact that light gets bent by glass, or glass bends the path of light because the light slows down in the glass. This is Snell's law. Okay, using the fact that glass will bend light, we want to look at an object like this. This is a lens. Okay. It's a concave lens. And we want to study how we can use this lens to actually focus images on a screen. So the cross-section of that lens is going to be this image here I have on the board. And this arrow to the left is an object somewhere in the distance, a distance O away from the lens. And every point on the object has a spherical source of light coming out, spherical light rays. So if we look at the tip, there's spherical rays coming out from that tip. We follow one of them along the horizontal, it will get bent by the lens and collect down here to the right. Another ray coming from the tip will move through the lens and not get bent at all. And then another ray coming from the tip will go down, hit the bottom of the lens and get bent exactly horizontally. And where those meet, an image, a real image of the object will come into focus upside down, a distance I away. So the equations we're going to study for this scenario is that the 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. Of course, that can algebraically be changed around to solve for the focal length in terms of the object and image distances. Okay? So we're actually going to, on the optics bench, we're going to create this scenario here and measure I and O and I and verify the fact that the thin lens equation is correct. In order to do that, though, we really need another independent way of measuring the focal length. And so let's do that in the next snippet. All right, now we have this as the thin lens equation where O is the object distance and I is the image distance, F is the focal length. If the object is very far away, we can say it's like infinity. And the thin lens equation here becomes this one. And 1 over infinity we all know is 0, okay? And then what happens is, in this scenario then, the where this object here is becoming close to zero, right? That's very close to zero, and what's left of the equation is this relationship, which tells us that the image distance is equal to the focal length. So what we want to do then is, if the object distance is big compared to the image distance, we can use the approximation that the image distance is approximately equal to the focal length. And so let me hold this lens up here. Let me hold up this lens, and let's walk it over to the board. And let's just say, let's look at this now. Look at this lens. And as I move it closer to the board, you can see that the room behind me come into focus on the board. Do you see that? So as this lens moves close to the board, the lights on the ceiling come into focus right about there. And this distance from here to here is actually the focal length, because the lights are so far away compared to the image distance. Again, if I start here and move in slowly, when the lights on the ceiling come into focus right there, the distance between the lens here and the board is the image distance, and that's the approximation of the focal length of this lens. And I can't do it with my hands tied here, but that length turns out to be, for this chubby lens here, that turns out to be a 5 centimeter distance. So the focal length, therefore the focal length of this lens is then, in this measurement I'm doing right now with my hand, that distance right there from the lens of the board right now is 5 centimeters, which is the focal length of this lens. Okay? Now, if I take the other lens, so the chubby lens is a 5 centimeter focal length. This lens here, you'll see, is a little thinner. And as I move it in closer to the board, look, I'm going to focus on the board now. You see right there, the lights on the ceiling come into focus. Again, if I move it away, see they're out of focus? As I move the lens in close, right there, that's the focal length of this lens. And this distance right here is actually 15 centimeters that we can measure, okay? All right? So this lens has a focal length of 15 centimeters. That's going to be important. We're going to need that. 5 centimeters and the 15 centimeters numbers when we go to the optics bench. In order to do this experiment, we take a lens, we take one of the lenses. In this case, it's the 15 centimeter focal length lens, and we mount it in this holder right here, and that's been done. And then what we're going to do is we have this light box here, which when the light box is turned on, it will project this crosshatch image of this arrow and crossbar down the optics bench here, down the line. It'll project from the light box through the lens and onto this screen here. And the distance between the lens and the screen is going to be the image distance, and the distance between the lens and the light box image projector is going to be the object distance. So that crosshatch pattern there that you see, this pattern right here, this crosshatch, is the actual object that will be projected. Okay? So I'm going to turn the lights out, and then what I'll do is I'll move, by moving I'm going to leave the screen and the light box fixed, and then by moving the lens, I will be adjusting the image distance, which is this distance here, and the object distance, which is the distance from the lens to the object, which is, again, this crosshatch pattern here that you see being projected out of the light box. Okay? So I'll turn the lights out, and then what I'll do is we'll observe that the image may not be in focus right away, but by moving the lens, I will be adjusting the distance from the lens to the screen, which is the image distance. And as that changes, also the distance from the lens to the object will be changing. And when I get to the focus point, then that's the point where I can then go in and measure the distance from the lens to the screen, which is the image distance, and the distance from the lens to the object, which is the object distance. And then I can get a physical experimental test of the thin lens equation to see if it's correct. And that's really what we're trying to do, is we're trying to test the thin lens equation and verify it. Now again, in the other earlier segment, we proved that this lens here that I have mounted in here has already been proven to have a focal length of 15 centimeters. And so now that we have that number, we can test the authenticity and veracity of the actual thin lens equation. Okay, so my next segment, it will be dark in here. We'll be looking at this screen, searching for the image to come into focus by adjusting the position of this lens. But before I turn the lights off, what I've done is I've put this meter stick here on the bench so that I can actually measure the distance from the object, which is the projected object out of the light box, to the lens. So you can see I have here this meter stick below. So the distance from this object here to the lens will be this distance here that I'm scanning. So it'll be that distance there. And the distance from the lens to the screen, when the image is focused, will be measured along this meter stick. Okay. So I'll be taking those measurements. But before I do that, I want to turn out the lights so I can actually see this object here which is that physical crosshatch there. I can actually see it get projected and come into focus on the screen. And I'll adjust the focus by moving the lens back and forth until I see that object coming into focus right here. Okay? All right. So that'll be our data that we take. The data will actually be the measurement from the lens to the screen, and which is the image distance, and the measurement from the lens to the object here. Okay, so we have the lights out now, and I'm going to come over here and turn on the. I'm going to hook up the cable here and turn on the light box, as you can see. Now the light box is lit, and the object that we talked about, that crosshatch pattern, will get projected through the lens, and then over to the screen, where it will hopefully come into focus. Now, as I move this lens this way, I'll see that image on the screen. I'll see the image on the screen go in and out of focus. Now, right there, the image is out of focus, but as I move the lens this way, you can see it coming into focus right there. See, it's in focus. Perfect focus right there. And so the distance, now with the image in focus, which is established by moving the lens back and forth, the distance from the light box, which is the object, to the lens is going to be my object distance, and the distance from the lens to the image on the screen is the image distance. And now, as I showed you, what I have below there, which is hard to see because it's dark, but right below here I have a meter stick on the bench. When I turn the lights on, I'll be able to take those measurements. Again, the distance from the object to the lens is the object distance, and the distance from the lens to the image is the image distance. Now, there's an interesting thing here. There's two positions for the lens where that image is in focus. As you can see, that image looks bigger than the actual crosshatch pattern on which is the object. So it's been magnified. And the magnification is actually the magnification is the distance from the lens to the screen, which is the image distance, divided by the distance from the lens to the object, which is the object distance. And the magnification is negative because I don't know if you should be able to see that arrow got inverted. It's upside down there, you see? Whereas originally the arrow was right side up. You see the vertical arrow, the tip of the arrow is down, and in the light box it was pointing up. So that's that's basically my measurement. When I turn the lights on, all I have to do is measure the distance from the lens to the object, this is the lens to the object here. And then that's the object distance. The distance from the lens to the screen or the image itself is the image distance. And so I'll turn the lights on now and make those measurements. Okay, now with the lights on, I'm going to measure the distance from the object here to the lens using my meter stick here below, and you can see that distance is going to be almost exactly 20 centimeters. If I look up now, I'll be looking straight up at my lens, and so looking down at the lens and down, I'm right at around 20 centimeters. So my data is, the focal length is, I already know to be 15 centimeters from my measurement in the other room on the board. So the object distance is approximately 20 centimeters. Okay. And my image distance now is going to be the distance from the lens. Put my meter stick right there. The distance from the lens to the image, it's the projected image in focus there. And that's going to be, that measurement's along here. And that's right at about 62 centimeters, about 61.8 up to around 62, say, centimeters to the screen. So again, from the lens to the screen, which is the image distance, is 62 centimeters. So that gives me this number being 62. Okay. Now, if I go like this, I go 1 over O plus 1 over I. Is that equal to 1 over F? Well, you just simply have to take 1 over 20 plus 1 over 62. Is that equal to question mark 1 over 15? And of course, that's something we can do, and you should verify how close this number is to this number, and see that the thin lens equation has been obeyed. See that the thin lens equation has been obeyed. Now, let me, could you turn the lights off again, Doctor? Yes. So we're going to turn the lights off again, and we'll see here, again, we're in focus there. You can see the inverted arrow, and if I move this lens, there's another position where that image will be in focus. So let me move the lens, and you'll see that image come out of focus. See, it's blurry there. It's going to get real blurry, and then it's going to come back into focus right there. It's going to come back into focus right there. A little hard to see. Yeah, see how in focus it is? If I go further, see how it goes out of focus? Come back, and we're back in focus right there. Okay. Now, that's called the conjugate position. And, okay, turn the lights on now. And you'll see that now what happens is the position of this distance here, which was used to be 62, is now 20 centimeters. So the image distance is now 20 centimeters, which we can verify here by, if we put that down there now, we can see that distance is now 20 centimeters. And the distance from the image distance is now 20 centimeters, and that's the distance from the lens to the screen. Now the distance from the lens back over to the object is now 62 centimeters, which we can verify. Okay. I can verify that is now 62 centimeters, and I come straight up to my lens there. So where this was originally the object distance, that becomes the image distance, and the image distance becomes the object distance. And you could see the sum of these two numbers is the sum of those two numbers, which will be equal to 1 over the focal length. Okay, but now that what you have is the image distance is smaller than the object distance, and so the magnification is the image distance over the object distance with a negative sign, and that's going to be a number less than 1, and that's why this arrow is so tiny now. You can see how tiny it is compared to before. Okay, so the other thing that we managed to verify qualitatively is that the magnification is equal to minus the image distance over the object distance. The minus sign is because the arrow which is up and down there gets inverted when you look at the image. The arrow's pointing up there. Now, in order to see the arrow pointing down, I'm going to go to the other conjugate position, which is, can you turn the lights out again? We'll see the arrow is pointing down there. You can see that it's pointing down, verifying the magnification equation. Okay. All right, so we're going to go back to just the chalkboard again for a second here, and I'll see you again in a couple minutes. Take our data, the object distance of 62 centimeters and the image distance of 20 centimeters. When we plug those numbers into the thin lens equation here, 1 over 62 is 0.016, 1 over 20 is 0.05, and 1 over 15 is 0.066. Of course, the sum of these numbers is exactly equal to 0.066. So it appears as though the thin lens equation works and is correct. And we have definitely experimentally verified the veracity of the thin lens equation, which is this equation right here. Okay? So if the thin lens equation is working, and we're certain about it, the other thing that we've verified is that the magnification is equal to minus I over O. This has been verified qualitatively. A little hard to measure that exactly, but you can rest assured that it's certainly in the right proportion. Okay, so there we have now utter confidence then that this equation right here is no longer a question mark. It's no longer a question mark. We can scratch out that question mark and say that yes, indeed, we are confident now that 1 over the object distance plus 1 over the image distance is equal to 1 over f. And we have determined this with great confidence now. So with that equation verified, The rest of your lab will be questions using this equation, and perhaps some ray diagrams that your instructor will send you, or some questions to do, and that'll be your lab write-up, the answers to those questions. But now, at this point, we can be happy and confident that the thin lens equation is correct. Okay.